we're going to talk about chapter 4, which are higher order ODEs, okay? And so very basically, we want to look at a differential equation. Well, let's remember what we did first of all with second order ODEs. So in chapter 3, we looked at second order equations of the form linear. So they're a function of x times y double prime plus another function of x times y prime plus a function times y, and it's equal to some inhomogeneous term over here. And we learned that there was a basic existence and uniqueness theorem, which said that if the p, the q, the g, and the f are all continuous on an interval, then there exists a unique solution to that problem if you have two initial conditions. If, I should say here, if the basic existence uniqueness theorem for this, we need two initial conditions. Let's say y at t naught is y naught, and y prime at t naught is y1 for t naught in the interval from alpha to beta. Because in order to have a unique solution, you're going to have the initial conditions to specify the unique solution. Okay. But in general, without the initial condition, you need two linearly independent solutions to specify the general solution of the homogeneous version of that equation. So the homogeneous version is where the function f, try to get this straight, where the function f is, let's do it this way. Okay. So where the function f is identically equal to 0. So second order equation, we needed two linearly independent solutions. And then we went on then we went on to study the homogeneous equation with constant coefficients. Actually, that's the first one where we studied to actually start to write down the solutions of the equation. Excuse me, so with the second order equation, we would find two solutions, y1 and y2, and then any solution of this equation could be written as a linear combination of those two solutions, as long as those two solutions were linearly independent. And remember, we said that for two functions, they're linearly independent if one is not a multiple of the other. But I told you that in class, I mentioned that in coming attractions, we would have to give a better definition. And we're about to need the better definition as we learn today. But again, we call some terminology. When you had two linearly independent solutions to the second order linear equation, you call those two a fundamental set. So they're solutions and they're linearly independent. That's what makes it a fundamental set. Okay. I'm trying to get this to be a little bit bigger. If I can, maybe, yeah, there we go. That's better. You'll see less of the page, but it'll be a little larger. Okay. Let's try it like that, maybe two. Okay, we'll try it like this. Okay, let's try it like this. Okay. All right, so now, so we said that a general nth order linear ODE is something that can be written in this form. Okay, so, well, not we said, I'm defining a general nth order linear ODE to be something that can be written in this form. So each derivative of y has a function of x in front of it, and then they're all added together. But notice it's linear because there's no function of y or its derivatives times another function of y and its derivatives. So it's got to be able to be exactly written in this form. If the g is not identically 0, it's an inhomogeneous equation. If g is 0, then it's a homogeneous equation. Okay, and remember that a little parentheses around something means a derivative. So this is an nth order derivative. If the first coefficient of the nth derivative is 0, then it's not really an nth order equation. So we can go without loss of, and it would just begin with the next term. So we could say that the coefficient of the nth order derivative is non-zero. You can assume that without losing any generality. So if we do that, then we could divide through by that coefficient. So you can always write an nth order equation, and here's where I ran out of ink before and had to change pens, and write it in the form, you have the nth derivative, and then every lower order derivative has a coefficient, which is a function of the independent variable. Okay, and we want to study that on an interval I. Now, to have a chance of specifying a unique solution to this problem, you know you're going to need some conditions. When it was a second order equation, we needed two conditions. This is an nth order equation, so we need n conditions. So generally, we think of those as being written as you specify the function and its first n, you specify the function and its first n minus 1 derivatives at some point t naught in the interval that you want to study. So when I write it this way, these things over here are just constants, they're numbers. Okay. And again, like we did in the second order case, yeah, it's not working well enough. Gonna just take a little time to get all this fit together nicely. Okay, so again, like in the second order case, when you have the nth order equation and n initial conditions, then the basic existence theorem is going to say, as long as the coefficient functions up here in this equation are continuous, so all the a sub n minus 1, and so on are continuous, and that inhomogeneous term is continuous, then that problem has a unique solution that satisfies the initial conditions, and moreover, the solution is continuous on that interval where all the ingredient functions were continuous. Okay, so now if basically we would love to be able to solve the nth order in homogeneous. If you're going to solve the inhomogeneous equation, you have to first solve the homogeneous equation. So this is where the right-hand side is equal to 0. But as a starting place, just like we did in second order equations, we'll start with constant coefficient. Then we'll learn variable coefficients later. Basically, we only learned how to handle those, except in a few special cases, by using variations of parameters. And we'll get a variation of parameters type formula for these higher order problems as well. Okay. Okay. All right, so let's see. So we want to study our nth order linear homogeneous constant coefficient ODE. Okay, so now we're taking all those A's to be constants. So how do you begin to study that? Well, just like we did for the linear equation, we guess a solution of a certain form. You guess it to be an exponential. You guess a solution in the form e to the lambda t. All right, if you do that, to look at what it does in the equation, you're going to have to compute its derivatives. So what happens when you differentiate that? When you differentiate it the first time, you get a factor of lambda. When you take the second derivative of y, you get another factor of lambda, so that's lambda squared e to the lambda t. And every time you take another derivative, you get another power of lambda. So the kth derivative has the kth power of lambda times e to the lambda t. All right, so if that, we know the algorithm now how to figure out all the derivatives. So we plug that into this equation that we want to study. So what does the nth derivative look like? It is lambda to the n times e to the lambda t. Now I'm going to put the e to the lambda t outside because each term I write down is going to have one in it. So I write down a lambda to the n, lambda t out here. Here's a lambda to the n that comes from this term. Then I write down my 8 sub n minus 1, the constant. And what happens when I take this derivative? Well, I'll get a lambda to the n minus 1 times e to the lambda t. So that's this term. And you keep going like that. When you finally get to the last one, you have a0 times y, which is just e to the lambda t. So you just have a plain a0 left. And all of that by the equation has to equal 0. But like we did before, we observed that e to the lambda t is never 0. So you can divide by it, and you get the characteristic equation. Now, for our second order equation, the characteristic equation was a quadratic, and we know the quadratic formula. So the quadratic formula tells you how to find all the values of lambda, and there were 3 cases: 2 real distinct roots, 1 double root, or 2 complex conjugate roots, and we worked out the solutions for all of those. Okay. But now we have an nth order algebraic. Notice again, this is an nth order algebraic equation. How do you solve those? Well, if you've played around with this a little bit in high school algebra, and you should have, and in college algebra, if you had to take it, you know that you can solve them, but there's no nice simple formula like you have for the quadratic equation. There are algorithms for the third orders and the fourth orders, but they're in general hard to write down, hard to remember. But we do have one tool from the general theory of algebra that says that it's called the fundamental theorem of algebra, in fact, that says every nth order algebraic equation has n solutions counting multiplicity. That means things can have you can have a root that appears 4 or 5 times, or any number of times, okay? So every nth order equation has n solutions counting multiplicity. The solutions either occur as real solutions, so in other words, they're real numbers, or if they're complex numbers, they occur in complex conjugate pairs. That happens so long as the coefficients in that equation are real, and all of ours will be. Okay. So we have basically cases similar to what we had in the case of the second order equations. Some roots will be distinct, some will not. Some will have multiplicity, higher multiplicity, and some will occur in complex conjugate pairs. So we have to learn how to handle all of those in solving these equations. Okay, before we get to that, we need another little bit of terminology for writing down solutions to our nth order equation. And that's how do you define linearly independent and linearly dependent for bigger sets of functions than just 2, like we've had before. So suppose we have a set of functions, n of them. Let's call them phi1 up to phi n. We say that they are linearly independent on an interval I if when you take a linear combination of those functions, so c1 phi1 plus c2 phi2, and so on, up to c and phi n, when you add all those together, that equals 0, implies that all the coefficients have to be 0. Okay, so that seems a bit strange, but let's look at that for a second. Let me try to help you focus in on this. Let's focus for a second on what happened in the case of 2 functions. What does it mean to say that 2 functions are linearly independent on an interval? So by the definition I just gave you, that says c1 phi1 plus c2 phi2 equals 0 implies c1 equals c2 equals 0. Gee, is that what we had before? Let's think about it. Let's think about it. Oh, sorry. And we say, I should have said this before I even went to the example. The set of functions are linearly dependent if that linear combination being 0 can hold with at least one of the C1s not equal to 0. Okay, so if they're not linearly independent, then they're linearly dependent. Okay, so if this linear combination being 0 says all the C's have to be 0, linearly independent. Anything else, linearly dependent. Okay, so let's go back to our example of 2 functions. So suppose phi1 and phi2 are linearly dependent on an interval I. Whoops, what happened to that? I lost it. Okay. Suppose phi1 and phi2 are linearly independent. Linearly dependent on the interval I. All right, then that means that if you look at this linear combination, C1 phi1 plus C2 phi2 of x equals 0, then at least one of these, for this to be linearly dependent, that means at least one of the C1s or C2 is not equal to 0, and that can hold. So let's say it's C1 that's not equal to 0. Then you rewrite this as phi1 C1 is equal to minus C2 phi2. And now divide by C1, which you can do because it's not 0, and you get that phi1 is minus C2 over C1 times phi2. That's a minus sign there. And this is just a constant. In other words, phi1 is a multiple of phi2. So that's what I said way back when, that for our when it's just 2 functions, linearly dependent means one is a multiple of the other. Linearly independent means one is not a multiple of the other. Okay. Now we need it for more than just 2 functions, and it gets a little more complicated. Okay. Whoops. Let's see. I wanted to do this page first. Okay. Is this set, let's look at this example. This set 1t squared, and ask the question, is this linearly independent on the interval from minus infinity to infinity? 1t squared linearly independent on the interval from minus infinity to infinity. Okay, so on the whole real line. So how do you check that? You write down C1 times the first function plus C2 times the second function plus C3 times the third function equals 0. And so C1, C2, C3 are just some constants. And you say this has to hold on all of R. And now you want to see, does that tell you that all 3 C's, C1, C2, and C3, all have to be 0? Well, let's check. If it's going to hold on at every point on every real number, then it has to hold at t equals 0. So what does that equation say at t equals 0? That says C1 plus 0 plus 0 equals 0. So that says C1 equals 0. Okay, so far we've got that C1 must be 0. All right, this equation also has to hold at t equals 1 because it has to hold for every real number. So let's see, that'll say, now we already know that C1 is 0. So that'll say that C2 times 1 plus C3 times 1 has to equal 0. So it says C2 plus C3 is 0. It also has to hold at t equals minus 1. So what's the equation at t equals minus 1? So C1 is 0, and then we have at minus 1, we have minus C2 plus C3 times minus 1 squared equals 0. Now we have these 2 equations, this one and this one, and now we have to solve them simultaneously for C1 and C2. So what does that say? Well, you can do it any way you like. I'm going to just rewrite this one. This one says C2 equals C3, and then use that in the first one. So by using that in the first one says C2 plus C3 equals 0. On the other hand, we know that C2 has to equal C3. So that will say C2 plus C2 equals 0. I'm just using what we know from this. So that says 2C2 is 0, so C2 is 0, but C2 equals C3, so C3 is 0. Therefore, the only solution is C1 equals C2 equals C3 equals 0. So that means that by definition, this set is linearly independent on R. Okay, if we had gotten a non-trivial solution, we had found values of C1, C2, and C3 that worked and weren't all 0, then the set would have been linearly dependent. Okay. Okay, now that's not a fun thing to have to do, to keep checking and checking to see if it's linearly independent or linearly dependent by the definition, because you can get into some awful big sets of functions that you have to check and look at. So we don't want to keep having to do that. So we're going to try to find a better way, but we need a little bit more machinery before we do that. Okay, so we say that a set of solutions, y1 up to yn, form a fundamental set of solutions for, this was the, get that equation back up. So double star H is the equation, the nth order homogeneous equation, linear with variable coefficients. Okay, so we have a fundamental set of solutions for that equation if each yi is a solution and the set is linearly independent. So you need two things. They all have to be solutions and they all have to be linearly independent. It has to be a linearly independent set. Okay, so our theorem says that suppose you have a fundamental set of solutions. Okay, again, that means they're all solutions and they're linearly independent to our problem that I just showed a second ago. Then any solution of that problem can be written as a linear combination of those solutions. So if you know a little linear algebra, a way to say that is this set of solutions spans the solution space. It's a basis for the solution space of the functions for the differential equation. If you don't know linear algebra, don't worry about it. Just this theorem just says that any solution can be written as a linear combination of the solutions that make up that fundamental set for some values of those constants. Okay, so that's the exact analog of that first basic theorem that I showed you, reminded you of, that we have for second order equations. Okay, the solutions of second order ODEs, if you remember, one way we could check if they were linearly independent or linearly dependent was by using the Wronskian. So generally checking a set of functions, just I'll show you a set of functions, say, are they linearly dependent or linearly independent on this interval? You have to use the definition. There is no other way around it. But if you say, here's a set of functions and they solve this ODE, are they linearly independent or are they linearly dependent? It turns out that the Wronskian will give you a way to check for that. What we have to do is learn how to write down the Wronskian for a set of n functions. We learned how to do it for 2, and we'll do that in section, I believe, 4.3.